So, now we should begin to talk about practical applications. In most cases, we want to know the resonant frequencies, for example, of the machine frame. We need to know it because the machine speed must not be equal to resonant frequency. For example, we use the steel beam. The hammer with force sensor is usually used for the excitation. The acceleration sensor is used for response measurement. The measurement will be triggered by the hit. We will hit the beam by hammer on one side and measure acceleration response on other side. Now we must set the trigger source to amplitude and set the amplitude trigger level. Usually we do not know the correct amplitude for triggering and we make the test. The best way is to measure the time signal with several hits and find out the value. I select the time signal measurement with frequency range 6400 Hz and 2 seconds signal length. Now I push start and I hit the beam several times. This is the time signal. I can see that -100 newtons is suitable level. I return to the trigger setting screen. I set the trigger level to -100 newtons. I also set the pre-trig to 25%. Now we make the initial measurement with FRF function without the accurate setting of windows. We will set it later. This is example of FRF setup. I start the measurement. The window waiting for trigger appears. Now I hit the beam. The initial graph of response appears. But it is preview, because we must set the windows accurately. Press the Graph Properties button. Set the View parameter to the time. 2 time signals from both channels are displayed. I make the zoom of signals. Then I push the spectral window button. Now we can shift the windows and change their length. Firstly, I set the transient window on channel 1. It should cover just first half period of the hit. Now I increased the length of exponential window on channel 2. The beginning is on hit time and the length I optically set according the signal. The length should not be too long. It should drop to the 0. We start the measurement again and we make the averaging. We can see the frequency response function. There are 5 resonant frequencies. The coherence is near value 1. It means all measurements in averaging were stable on these resonant frequencies and we can trust and use them. What is the background of this graph? The y-axis is in G per Newton. It tells us how many Gs we get if 1 Newton force is applied. The beam is softer on resonant frequencies. It means 1 Newton excites there more Gs than on other frequencies. And that is the reason why we use FRF measurement. We want to know the resonant frequencies. For example, we need to know the resonant frequencies of machine frame. Any of them must not be equal the machine speed, because the small force would excite high vibration, and the force on speed frequency, it is the unbalance. It means small unbalance could cause a high level of vibrations. Just a small note about coherence. If we want to know how stable are measurements, we need to measure more than once. If we make just one measurement, then it's not possible to tell how it is stable. We must compare more measurements. For one measurement, the coherence is always equal 1. That is why we always use the averaging. Let's suppose some FRF measurement. On the graph is the theoretical accurate FRF function. We can see 2 resonances and 1 anti-resonance. In real situation, every signal contains the noise, and it distorts the results. We can suppose the noise on the input or on the output. You can see the values with no noise. The response value is 2. Every input value is multiplied by 2. Now you can see accurate values on the input, the same as in example with no noise. But the output is not accurate equal to value 2. It means the output contains noise. Now you can see not accurate values on input and accurate values on output. In this case, we talk about noise on the input. Of course, we can have noise on both sides. The accurate FRF is on the left, but in the FRF parameters you must select between H1, H2 and H3. The comparison between accurate FRF and H1 is in the middle. You can see that H1 is accurate in anti-resonance, but not in resonances. The comparison between accurate FRF and H2 is on the right. You can see that H2 is accurate in resonances, but not in anti-resonance. The H2 is always greater than H1. The H1 is used for noise on input. The H2 is used for noise on output. The H3 is just the geometric average. It means H3 equals square root of H1 times H2. It is something in the middle. In vibration diagnostic, we are always interested of resonances, and we have noise on the output made by mechanical response. That is why we always use H2. Next note is about physical quantity of measurement. The excitation is always force in newtons. When the response is in acceleration, then FRF is called accelerance. If the response is in velocity, then FRF is called mobility. In case of displacement response, we talk about compliance. So we get G divided Newton, millimeters per second divided Newton, and micrometer divided Newton. Also, the inverted functions are used. We talk about dynamic mass for acceleration, mechanical impedance for velocity, and dynamic stiffness for displacement. All these FRF are available with any type of sensor. We can use the acceleration sensor and we can just recalculate FRF to velocity and displacement. All recalculations are just integrations or derivations. We just talked about FRF as real-type function. It was better for understanding, but the FRF is complex. It means it has amplitude and phase for each AC line. Amplitude value we explained, it is the gain, but also the phase on the input is changed to the phase on the output, and the difference between them is the phase change value in FRF. The phase changes of 180 degrees through every resonance. But for vibration diagnostic is the amplitude much more important. The FRF measurements are widely used in modal analysis, and here is big advantage of VA5. The standard measurement hardware for modal analysis is big and difficult to use in field. It is designed for laboratory use, but VA5 is small and easy portable. You can measure all required FRF in all points and export then in UFF format. And then in laboratory you just import these files to your modal analysis software. And it is everything of basics what you should know about frequency response function. Thanks for watching.